Thank you. Right. So today we talk about the analog of Garland's theorem for Lie groups. And this will be based on joint work with Uri Bader. Yeah, so let me start with the statement. And also with first chapter reduction to the really hard case. All right, so what's the theorem? Theorem A is that SLNZ has property Tn minus 2. And note the brackets. So this means that if you look at the cohomology of that group in degrees up to n minus 2, and you plug in as coefficients the unitary representations without invariant vectors, then it will be 0. But that group, and we'll talk about this a little bit in the next lecture tomorrow, will have interesting cohomology with the trivial coefficients. So that's the best you can hope for. And well, more generally, let me stick mostly with this SLN case, but more generally, any lattice in a simple Lie group, maybe finite center, has Td minus 1, where D is the rank of the real rank of the group. So yeah, let's put it here. All right. And the theorem B, I mean, this is the analog of Garland's theorem. The difference to lattices in non-Archimedean groups was there we have the other brackets. There was not even cohomology with trivial coefficients, so that's different. So there was this question yesterday, what happens if you have products? And can one even say something about a situation where you have, say, products of rank 1 groups? So you have higher rank, but you don't have property T. And you don't have a statement like that, but you have one statement that I want to present. So let gamma be a lattice in a semi-simple Lie group G, again finite center, no compact factors. And let pi be a unitary G representation. And then what you can say is that the restriction map from the continuous cohomology of G with pi coefficients, so just restrict co-cycles to gamma, and you get a map to the gamma cohomology. Q pi is a gamma unitary representation, and this is an isomorphism below the rank. All right, so this looks a bit different. Again, note there is no assumption on property T here. It's a very general statement. It can be concluded from in the case of a simple Lie group, it can be easily computed from that theorem. It's maybe not obvious to you right now how to conclude it, but it can be easily concluded. But it's true in general, even without property T. And it uses somehow, I will not talk about this theorem, but since the question came up, so this is what uses property tau. And somehow like this combined work of Selberg, Burger, Sarnak, Clausel, that all, somehow this very strong property tau statement that we have, that goes into that theorem. And of course you might ask for more. You might ask for a statement about the cohomology of gamma with respect to a true gamma representation that does not necessarily come from a G representation, and ask about the cohomology of that in that very general case. And so the statement would be the conjectural statement, but that requires something stronger than this property tau statement, is that if you have a representation pi that does not, there's no sub-representation of that representation pi that continuously extends to a G representation, so it's really completely just a gamma representation. Then you have a similar vanishing statement for the cohomology of that gamma being a lattice in a semi-simple Lie group. Not even with Kazhdan factors, just rank 1 factors. But that's a conjectural statement. It's based on a conjecture about unitary representations that I think is relatively hard. But somehow, this is what you can say in a situation where you don't have property T, but you still get from property tau some spectral gap statements that... sorry? Oh yeah, I need irreducible. Thanks. All right, but today I want to focus on that theorem, on the analog of Garland's theorem. And let's start with the easy part, which is almost done with what we discussed so far, which is the reduction to the non-uniform lattices. So somehow the uniform case is easily handled now, but let's discuss it another way. So let G be as in theorem A from now on. And then we have a huge input that brings us very close already into that area, which is a theorem by Vogels-Zuckerman from representation theory. And I will not discuss the proof of that, because that's a proof that requires this Lie algebra cohomology that I briefly mentioned, and analyzing the Lie algebra complex and using some facts about representations of the Lie algebra of the semi-simple group. But it gives us a very clean black box. It says that if you look at the cohomology of gamma, sorry, the cohomology of G, I want to say, with respect to a G representation now, which is irreducible, then this is 0 for I smaller than the rank, and every irreducible unitary G representation. Okay, maybe I didn't write it, but let me also say that this theorem A, it's not only true for the lattices, also the ambient Lie group G has this property Tn minus 2. And the proof of theorem A is switching back and forth between G and gamma. And so we start with G, which is easier, and take this theorem for granted. So for every irreducible unitary G representation, we have that, but irreducible is somehow in that proof essential. And so how do we use what we discussed now to quickly somehow go to all representations here? If you have a G representation which is not irreducible, then there is a decomposition that we can use into irreducible. So the corollary of that theorem with what we have is that we actually have this property that we have the vanishing here for every unitary representation, which is just short for T rank G minus 1. And the proof is, so if you have this pi, there is a decomposition in irreducibles.
Sorry?
Yeah.
In the theorem by Wagner-Zuckerman shouldn't be trivial.
Yes, 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 because we have these brackets. Thank you. Oh, that's great that every little mistake gets caught here. That's really good. So we have a decomposition into irreducible. G representation. And I didn't discuss this construction, so if you haven't seen it, you might know from representation theory, let's say of finite groups, which is the easiest, that you can always get a decomposition of a complex representation of a finite group into a direct sum of irreducible decompositions. In the unitary world, there is something similar, but somehow direct sum has to be replaced by something more complicated, and this is this direct integral decomposition. So this construction generalizes a direct sum of finitely many irreducible decompositions. It also generalizes a Hilbert sum of infinitely many irreducible decompositions, but it's even more general. So this is like the space of sections in a measurable bundle of irreducible decompositions, which I don't want to somehow discuss now, but it's there. And the thing is that the ordinary cohomology does not respect this decomposition. So if you have a sum of two gamma representations and you take its continuous cohomology, then it would be just the sum of the two cohomology groups. But if you have that construction, it's not respected in the sense that, for example, if you have that each of these pi x has vanishing cohomology, it doesn't follow that the cohomology of this pi has vanishing cohomology, for example. But what does respect this kind of integral decomposition, at least the vanishing, is the reduced cohomology. So in quotation mark, respects, at least you can read off the vanishing. And an example actually was yesterday mentioned by Antonio when he said, oh, these nilpotent groups, they satisfy this, not this property, but this property when you replace cohomology by reduced cohomology. And actually that's a good example, because if you take this decomposition and your G is nilpotent, then the ordinary cohomology of all these pi x will vanish. But definitely not the ordinary cohomology of that pi. So in general, it doesn't respect it, the ordinary cohomology, but the reduced one does. And nilpotent groups would be a case where you see it somehow to the maximal extent that it doesn't respect it in general, the usual cohomology. Okay, but this does, and therefore, using this theorem by Vogan-Zuckerman, we have that this is 0, or let's write I, for I below the rank, and every pi with no invariant vectors. And then, as we've discussed, to a large extent now, we know that this would, because we have it for every pi, now we want to say then we get the same statement for the cohomology, the ordinary cohomology. We do this ultra power technique. Remember that if we talk about this property with these brackets, we have to have that the group G has the ordinary property T to conclude that. But somehow we can assume that the rank is at least 2 here. Otherwise, it's not an interesting statement. So we might assume that G has property T, and then we can conclude I mean, there is no statement here if the rank is 1, right? Then it's a statement about the 0th cohomology, and the cohomology in degree 0 of a non-trivial representation without invariant vectors is 0. So it's obviously true, but it's not an interesting statement. So we might assume rank at least 2, and so we may assume that G has property T. Yeah, there was a question?
What does irreducible mean?
Irreducible means that there is no non-trivial closed G invariant subspace in HP, because if you have such a subspace, you could act G just on this, and this would be a sub-representation.
Yeah. And then so
non-trivial means it's not the trivial representation where G does nothing.
the trivial representation is obviously reducible, right?
Yeah, it is irreducible. It's just C, just the complex numbers, and G acts trivially on it. Just C, and I'm assuming I exclude this representation C. Yeah. All right. So therefore, by this ultra-powered method, we get this for the same thing here. And okay, I didn't do the ultra-power technique for G. I did it for discrete groups only, as you noticed. So there are two ways. Either you do it in this more complicated way where somehow the ultra-power is defined in a more complicated way, or you can play with a co-compact lattice. And so there is a way to, it's not a problem. All right, so this gives us this higher property T for the ambient group G. And now we want to say something about the lattices in G. And the easy situation is when we have a co-compact lattice. And there is something in the general theory of cohomology of locally compact groups, which is called the Shapiro isomorphism. So no semi-simple Lie groups needed. This is really about lattices in locally compact groups, co-compact lattices. And then we can compare the cohomology of gamma and G in the following way. Let pi be unitary gamma representation. And then the cohomology of gamma in pi in all degrees is isomorphic, and there is a natural map that I will also explain a little bit to the G cohomology. And now you have to take the induced representation that we discussed. Okay, so the star indicates this is true in all degrees. All right, so let's just assume that this is true. But I will talk a little bit about how to prove this theorem, at least about the map. But we have now a corollary out of this theorem here. So consequence so again, G is as in theorem A, and now gamma is co-compact. So sometimes I might use also the term uniform without noticing. So co-compact is also called uniform. It's the same thing. And then gamma has T rank G minus 1. Yeah, and how do you do that? Well, you want to look at the cohomology. So you have proof is a one line. So given is a representation without invariant vectors, because we're talking about this kind of property T. And then if you induce it, and I think we discussed this already, if you induce it, somehow the G invariant vectors of the induction are isomorphic to the gamma invariant vectors of pi. So also the induction has no G invariant vectors. And this means I can apply the theorem to say that this cohomology is 0 in the appropriate range. But now the Shapiro isomorphism tells us that this is just this cohomology, and so we're done. Okay. All right.
The sub C should be H by sub C like G thing.
I promised in the first lecture that you eventually forget this.
Yeah, but if you notice, then yeah. Right. Okay, so you see basically, of course, assuming quite substantial input here, we already had the tools. to quickly conclude now this theorem for the co-compact case and for co-compact lattices. So let's see. Let's go to the non-uniform lattices and let's discuss what's the problem here. I mean, because the only thing that seems to be problematic is this Shapiro isomorphism, which is stated for co-compact lattices. And let's study what is the problem with this in the non-uniform, in the non-co-compact case. Yeah. Okay, so there I need a cocycle, and cocycles I can never remember where the inverse is. So let gamma be lattice, uniform or non-uniform. Let's pick a fundamental domain in G and then there is something called the lattice cocycle. And the terminology might be a bit confusing in this context because, I mean, we have lots of cocycles because we're talking about cohomology all the time. But there are also kind of ergodic theoretic cocycles, non-abelian cocycles. They are called cocycles. And you can view them actually as cocycles in some non-abelian cohomology, first cohomology. But I don't care about this interpretation. It's just what I write down. It's a map from G times X to gamma. And at G comma X, we will declare it to be gamma if G minus X gamma lies in the fundamental domain. So I can put this away. I just, at one point I figured out where the inverse has to be. So I had to copy this. So you move your X with G outside the fundamental domain, and then the value gamma tells you, yeah, how to move it back, basically, into X. So that's called the lattice cocycle. It had a certain cocycle property, not so important for us now. But if you have this C, you can write down this map on the level of the cochain complex. It won't depend on the choice of the fundamental domain in cohomology. The map on the chain level complex might depend, but not on cohomology. Okay, so how is the map? So first of all, we should look again at this induction. So the induction, what is it? Let's remember. This is a unitary representation on the following Hilbert space. It's an L2 space of functions from G to HP, to the underlying Hilbert space of pi, that satisfy an equivariant condition. And they also satisfy these functions in L2 condition. This 2 is a bit misleading because it's not L2 on the whole of G. It's actually L2 on a fundamental domain, or equivalently on G mod gamma. So sometimes people indicate that's not the usual L2 by doing these brackets. But if you choose a fundamental domain and you don't care about the action so much, seeing the action, you can really write it as an L2 space from the fundamental domain to HP, somehow dividing out the gamma action. And then it's really L2 functions from X to HP. The only thing is that it's easier to write down the action in that formulation. If you write down the action here, well, you use this cocycle. But as a space, this is the space. And what is the Shapiro map now?
Sorry, what is the regularity of the lattice cocycle? Is it something measurable or?
I didn't. Here. Say again?
What is the regularity of the lattice cycle? Is it just measurable or?
Yeah, measurable. Yeah. Choose a measurable fundamental domain. I mean.
Okay.
Yeah.
Thank you. And define it just almost everywhere.
Well, you can define it everywhere.
Everywhere? Okay, I see. So the fundamental domain is like strict.
Yeah.
Okay, thank you.
Yeah. Okay, so the Shapiro homomorphism, how would it look like? Homomorphism on the chain level or co-chain level. All right, we're going from this to the continuous cohomology, and now I plug in this. Okay, so what do? We start with a co-cycle here, and we map it well to a function on tuples of G. So we have to say where does G0 up to, let's say, Gn go to. It goes to an L2 function on X, so another function here. And what is the function? Well, you take your co-cycle F, and now you plug in your lattice co-cycle. Okay, now I want to close every bracket. So, 1, 2, 3. Right, this is the map. So F is a map on tuples of elements of gamma, and you map this to an L2 function. And what's the L2 function? Well, you plug in this. Each z gi, x gives you an element in gamma, which you can plug in F. And now there's something to check, and it's annoying to check that this respects the equivariance. There you need this co-cycle property of this lattice co-cycle, and that it's a chain map is actually quite obvious. But that it respects this equivariance is something, it's a little annoying calculation. But that's the homomorphism that induces this here in the co-compact case. And let's look at this map. Now, why is it important that it's co-compact? Or what might be a potential problem? Potential problem is that, I see the time. Right, so why is this an L2 function? In the co-compact case, it is. And why is it? Because if you plug in a fixed element G into the lattice co-cycle and view it as a function on X to gamma, then this has finite image. And why is that? Well, if you have a co-compact lattice, we can take a relatively compact fundamental domain, and then you move that fundamental domain with that fixed G, still something compact, relatively compact, and you can cover it with finitely many translates, with finitely many gamma translates. And this is the range of this lattice co-cycle. So there, if you range through the X for a fixed G0 up to Gn, there will be only finitely many group elements in gamma appearing here. So this is like a step function. And it's definitely L2. But if it's a non-uniform lattice, this is no longer true. There will be infinitely many gammas in this image. And then it's completely unclear how to control the L2 condition here. It's just There's no way somehow. And in fact, you see, let me put this as a remark. So if gamma is not co-compact, the problem is not that this map is not an isomorphism. The problem is, and I didn't prove that it's an isomorphism, I'm just giving you the map. The problem is not that it's not an isomorphism, the problem is the map is not even well defined. There is no map. So for gamma non-uniform, the Shapiro map is not well defined. Sorry, it's a bit squeezed here now. Okay, and now let's offer a solution to this problem. And the solution is called polynomial cohomology.
By the way,
Yeah.
so even if gamma is non-uniform, like if it has only finite many walls around the fundamental domain, then it should be good as well. Like I'm imagining SL2Z inside SL2R, for instance. I know that it's not like
Yeah.
but it has like finite many walls in its fundamental domain as well, right?
No,
But that's it.
it's not good enough. The problem is the cost.
Yeah, yeah. Okay, let me define polynomial cohomology and why it offers a solution out of this. So let L be a word length function, or you can also take the reals, doesn't matter. Be a length function on gamma. Right? You can take a finite, all the groups we're talking about are finitely generated, so you can take the word metric and can take the usual length. And then we define a subcomplex in the bar resolution. And you can also take the invariance, or you can take it afterwards, it doesn't matter. Too many stars. And what is it? It's those f's such that there exists a constant which might depend on the f, and also a k which also depends on the f, such that there is a growth condition. So if you take f of gamma 0 up to gamma n, it takes values in this unitary representation, take its norm, and then it's bounded by this constant, and then you sum up the lengths. Now this, let me write this properly because that's an important condition. Need more space. So you sum up the lengths of the gamma 0 up to gamma n and take it to the kth power. So basically there is a polynomial bound on the growth of this cochain polynomial in the lengths of the entries. And this is for all gamma 0 in gamma n in gamma. So this is a subcomplex of the bar resolution of the that computes the group cohomology.
Excuse me?
Yeah.
Just to be sure, what do you mean by length function?
Take, let's say gamma is finitely generated, and just take the word metric.
Okay.
And then the length function would then be.
It can be more general than that?
This is what we use actually here.
Okay.
So
The word
yeah, just think of the yeah. It can be, I mean, you could apply this definition more generally, but for our purposes, this is it. And then the definition of the polynomial cohomology is, of course, the cohomology of this subcomplex. Yeah. So where does this polynomial cohomology historically first appear? It appears, although if you look at the paper, you might not recognize it, but it came up in the work of Alan Conant and Moscovici on the Novikov conjecture. So that's an instance where, at least to my knowledge, I see the first instance of a cohomology that has somewhat a polynomial growth constraint use. Maybe there are earlier ones, I don't know. And if you look at the paper again, it might look a bit different, but this is somehow the historical origin of that polynomial cohomology. And it sits naturally in between cohomology might null. Well, first of all, there is an obvious map to the ordinary group cohomology. Just forgetting that the cochain is bounded in that polynomial sense. So this is the natural comparison map to the ordinary cohomology. But you can also put stronger growth conditions on here. You could, for example, say, well, the whole thing should be bounded. And then what you get is bounded cohomology, which you might know. And you might have seen, I mean, it's a huge question in bounded cohomology, actually formulated for G, not for gamma, but never mind that. It's a very important question in bounded cohomology when this comparison map from the bounded cohomology to the ordinary cohomology is an isomorphism with huge implications for rigidity theory. And somehow this polynomial cohomology sits in between, and will have the advantage that this is much more often an isomorphism, also for discrete groups. This, for discrete groups, is basically never an isomorphism. All right. I have 15 minutes, right, so it's not so bad that I thought.
Is this an inclusion?
No map here is in general an inclusion. It's just a natural map. Actually, that map from here to here, well, okay, it might be an inclusion, yeah. No, but there's no general statement. Yeah. Also not this one, no. There's just natural maps, and in general we cannot say something about the injectivity or surjectivity for all groups. But that will be the question in a few minutes, so it will have an important consequence for the question of the existence of a Shapiro isomorphism for non-uniform lattices, whether this is an isomorphism. But maybe before, when we discussed cohomology, I made a big deal that, okay, you can compute it in various ways, and there are all kinds of resolutions. And that's not important maybe for the discussion, but somehow I thought you might want to know whether for this polynomial cohomology there's only a definition in terms of the bar resolution, or there is something more flexible, right? As we've seen, cohomology can be defined with this standard resolution, but there are various ways to compute it, various ways to somehow express it. And here is, so this is like a little digression for those who know some homological algebra. If you have the ordinary group cohomology, you can express it as a derived functor over the group ring. Such an X of the group ring. If you don't know it, never mind. It's just a small digression. I will go on from that. But I think it's interesting, nevertheless, to mention that. If you have the polynomial cohomology, there is also a quite abstract way to express it. It will be also an X term, but now in a different algebra. Where this S gamma is a Fréchet algebra, and it is a completion of the group ring with respect to a family of seminorms. Well, it's actually norms here. So what is the family of norms? If you take, let's view an element in the group ring as a finitely supported function on gamma. And then there is a norm indexed by a natural number k, where this is just the sum over all gammas, absolute values. So this would be the L1 norm, but now you take this length function into account and do this. So can complete with respect to a family of norms, even semi-norms. And what you will get is a Fréchet space containing the group ring as a dense subset, and it will be actually still an algebra. And then these guys here become modules over this algebra, and you can express it like that. And I wanted to mention that because I could imagine that some of you have seen similar growth conditions previously. And for example, if I would take instead of that, I'm not writing this really, let me put it just in red. So you could take squares here and take kind of an L2 norm. And that is something that some of you might have seen. If you do that, you can also complete your C gamma. If you complete this for each individual k, you will get a Hilbert space. And it will not be an algebra. And if you do the completion with respect to all these norms, you will get a Fréchet space, which is not always an algebra, but it is an algebra in an important situation, namely if the group has rapid decay, the rapid decay property. So maybe some of you have heard rapid decay property RD. If you have the rapid decay property and take the completion with respect to these norms, then rapid decay means that the algebra that you get, and it will be an algebra in this case, it's called the algebra of rapidly decaying function on the group. And rapid decay property means it's an algebra and it's sitting inside the reduced C-star algebra. So if you know that, bear in mind, this is something different here. We're not taking L2. We're doing what we have here, invite, and this will give you an algebra. So it looks like there is something with rapid decay, but it looks somehow close, but it's something else. So just to remark for those who know that property. Back to Shapiro now. Now I have to clear some. All right. So the fact is, the Shapiro map, or the restricted Shapiro map, where you don't start from the bar resolution of gamma, but you only start from this subcomplex. And go to the cohomology of G. Is well defined in our setting. And when I say in our setting, I mean this is not a general fact about locally compact groups. This is something that again uses semi-simple. And what's the deal here? So you see the problem with the Shapiro map was that somehow we wanted, at least we need an L2 function here. And somehow if this range is over infinitely many gammas, we had no control. Now if we had a control on the lattice cocycle, in the sense that somehow we have a control on the length, right? So I have this function, this range is in gamma, and now I take the length of each group element. If I had a control on this somehow, I'm a bit vague, then since we start with the polynomial cohomology in a polynomial chain, if we have a control on the elements, on the lengths of the elements that appear here, we have a control on the size of this f. And then it's actually possible you have the correct control on this cocycle, which is something that we use. It's also a non-trivial fact, and this is something that uses semi-simple groups. Plus the control, the polynomial control on f, means you can show that what you get here is an L2 function. Okay, so I'm not writing it all down, and it requires some estimates, and you have to be precise, but it is well defined in the setting of theorem A.
But you have the same coefficient here? Or
oh, sorry, yeah. Thanks. So, yes, it's true in rank 1. This doesn't use higher rank, but it uses simple Lie groups or semi-simple Lie groups and some knowledge on the domain.
Don't you need integrability for the lattice?
Yeah, maybe you want to exclude SL2R,
Yeah.
but other than that, I think we're fine. Oh, maybe we need also go to. Okay, there are some low-dimensional cases that, but it's definitely true for 4-dimensional hyperbolic space, right?
I'm not sure.
Let's say it is. All right. So what's the theorem now that that we show? Okay, I try to put the whole theorem into a diagram. So here we have the ordinary cohomology. We're interested in a substitute of the Shapiro. Here we have the polynomial cohomology. Here we have this natural comparison map. Then here we have the cohomology of G in the induced. I said that this Shapiro is now well defined. What I didn't say is that you can actually do the polynomial cohomology also for continuous groups, and actually there is a factorization of that Shapiro to the polynomial cohomology of G So there is something like that, and there's a natural map here. So I'm just saying this is the map that you probably understand now, but it actually factorizes over something called also polynomial cohomology of G. It's very similarly defined, but I didn't want to avoid. I wanted to avoid some subtleties there. So we have this, and we want somehow to go from here to here. So what can we say? So what happens is this is an isomorphism in all degrees. That's part of the theorem here. This is an isomorphism in all degrees. In particular, this Shapiro is an isomorphism in all degrees. This is not an isomorphism in all degrees. This is an iso in degrees below the rank. And so you want to go from the left-hand side to here to somehow, if you remember, to conclude the statement of theorem A for the lattice from the statement for the group G that we have. So that's why you want to compare the two. You somehow cannot do it in every degree, but you can do it in the degrees that are relevant to us, right? We only want to show vanishing theorem below the rank. So somehow this map here, which is somehow not so clear how to define it on the chain level, but you can just say, okay, I go here and I go here, right? That's my map, and this is an iso below the rank. So as soon as we have this theorem, theorem A follows. So what we have to understand is somehow, where does this come from? Why is there an isomorphism on the polynomial cohomology to the ordinary cohomology? And this has a geometric reason. Now I'm anxiously looking. Yeah, I think speakers before me took extra minutes as well, right? It's just fair that I... Why should you have it better with me than with others? All right. Okay, there I need some indices. So the reason for this is that we have a good understanding of higher filling functions. Again, this is our focus next. And the reason for this is an understanding of higher filling functions for arithmetic groups. Okay, so I know X was a fundamental domain. Now it's something else. Let X be a Riemannian manifold or a simplicial complex. Some nice space. Not too wild. And then one can define filling functions. If you note the in functions for groups, this is like the higher dimensional analog, but I will formulate it a bit more geometric maybe, less combinatorial. So let alpha be a singular cycle. I'm looking at the singular homology now. Even if I have a simplicial complex, I'm looking at a singular homology. And I'm looking at a singular. And for technical reasons, I need a Lipschitz cycle, so something that's Lipschitz on standard simplex to the space as a map. Let's say d-1 cycle in X. And then one can define the filling volume. So that the goal is here is to solve an isoparametric problem in your space. You want to fill that cycle and put this into this definition. So you're looking at the optimal filling. You're looking at the infimum over all the singular Lipschitz cycle. Let me just use this notation. So again, these are singular chains, and I'm looking at those that satisfy a Lipschitz condition, and I can tell you right away why we want this, because we want to take some volumes. So there's a natural notion of volume. If you have a Riemannian manifold, it comes from the Riemannian measure. If you have simplicial complex, you just take the d-dimensional Hausdorff measure, but you can somehow, if you have a cycle, there's a natural notion of volume. And you're looking at all the chains that fill this alpha and take the minimal volume of those. And that's the filling volume of alpha. And to get a function on your space, so V is now a positive real number, V stands for volume, and now put this into a function in the following sense. We take the supremum over all d minus 1 cycles whose volume is bounded by V, and then look how they are filled. So if, and usually we look at this situation when X is contractible, because if it's contractible, if you have a cycle, it can be filled at all, right? Otherwise, it might not be even be fillable. But we're looking at a situation where it can be filled, or highly connected at least. And then we're looking at this thing. So if this is polynomial in V, it means that if you have a cycle of volume V, you can always fill it like with some cycle of constant times V to the K. And if you have, yeah, I'll take 2 more minutes here. And now if you want to define this notion abstractly for groups, you can do the following. If gamma acts on some X, proper and co-compactly, then you can define the filling function of gamma as the filling function of this X. And now the thing is, this will depend on the choice of X. But with the right, you take somehow the same equivalence class of function like you would always do in any setting where you look at quasi-isometry invariance. So asymptotically, this does not depend on the choice of X on which gamma acts properly co-compactly and, let's say, contractible X. Can take any such X, and the asymptotics of that will be well defined, and therefore it makes sense to define it as the filling function of gamma. And this will be a nice invariant, will be a QI invariant, quasi-isometry invariant, and well defined. But co-compactly is important here. And all right, yeah. What are you saying, David?
Saying maybe finish what you have to say here in your last lecture, because I suspect you want more than 5 more minutes, and we're gonna.
No, I know I won't need more than 5 more minutes.
So even 5 more minutes more or less eliminates the coffee break.
All right. All right.
Maybe spend the first 10 minutes.
Yeah, I'm happy with that. At least we have this notion. And let me just finish, and I will write this on the board next time, that the thing is that if you have a ket 0 space, then this will be a polynomial function. That's a general theorem by Gromov and Wenger. So if you have a co-compact lattice, it acts on the symmetric space. It's a ket 0 space. So this will be polynomial in all degrees. And the thing is now, if you have a non-uniform lattice, this will be not polynomial in all degrees, but it will be polynomial below the rank by a theorem of Leutzinger and Young. And that will somehow give us, or this will be the major input somehow in the comparison of those 2 cohomologies. So yeah, let me say a few words at the beginning of next lecture.
Question for Roman.
At least questions that don't ask him to start his next lecture now.
So are you taking the real coefficients for the
for the filling functions, I'm taking the integer coefficients. I'm taking integer, yeah. So you could somehow, this was a bit more geometric definition. You could just somehow define it more combinatorial by looking at the cellular chain complex of X with integer coefficients and then ask with the usual L1 norm given by the basis of cells, asking about, yeah, how can you fill there? But this would be about integer coefficients. For the application to this, you might somehow think, oh, but somehow we're talking about unitary representation. Everything is about R or C anyway, so might it be possible? There is a small thing in the proof where I don't know how to go around with like filling functions, Hayden functions over the rationals, but it might be just that I'm too stupid. So we're using this for integer coefficients.
Other questions? If not, let's thank Roman again.